purpose of this video is to teach you about gases. So we have the kinetic molecular theory for gases. This means there are three parts to it. The kinetic molecular theory is that particles in gases are small, hard spheres with insignificant volume. Gases, with the kinetic molecular theory, states that the motion of the particles in a gas is rapid, constant, and random. So that means that the molecules are moving around very fast. Okay? The third part is that all collisions between particles in a gas are perfectly elastic. So that means that no energy is exchanged between the different gas molecules. Gas pressure is the result of simultaneous collisions of billions of rapidly moving particles. So because these particles start moving back and forth and running into each other multiple times, that pressure of the gas molecules pushing down and hitting different things, that is what causes pressure, and pressure is a force. Okay, so what is pressure then? Well, pressure, we can have gas pressure, which is the force exerted by a gas over a surface area. So how much gas is pushing down, how much air is pushing down on my board, on me right now, that is my gas pressure. If there's no pressure and no particles, that's considered a vacuum. Okay. At this time, we'll either do a demonstration of an item in a vacuum, or if you're at home, you can YouTube shaving cream or marshmallows or various things in vacuums and watch to see what happens to them and why that happens. Okay. The units on pressure, those are going to be, we have standard pressure. Standard pressure is 1 atmosphere is equal to 760 millimeters of mercury, which is mmHg, because that's the elemental symbol for mercury. mm for millimeters. We can have 760 torr, or we can have 101.3 kilopascals. Kilopascal, so that means the base unit is a pascal, and a kilopascal is 1,000 pascals. Okay? Like I said, these are our standard pressure units. So when it says at a standard pressure, these are the units that we will use, depending on if we want to match up atmospheres, millimeters of mercury, torr, or kilopascals. Okay, at this time I'd like you to get familiar with these. Hopefully you have done the Intro to Gases worksheet and you already are. We're just going to quickly convert 3 atmospheres to millimeters of mercury. To do so, we need to use a conversion factor just like we did for metrics. And we're going to convert using that 1 atmosphere is equal to 760 millimeters of mercury. So go ahead and do that. So now you have probably figured out that 3 atmospheres is equal to 2,280 millimeters of mercury. When we round that to the correct number of significant figures, we are at 2,300 millimeters of mercury. Okay, now let's try one more conversion. We'll convert 1,520 torr to kilopascals. Again, we need to determine what our conversion factor is going to be. This time going from torr to kilopascals. We have numbers in both places, and we need to reflect that in our unit conversion. So go ahead and do that at this time. Okay, you should have got the number 202.6 kilopascals. We have 3 significant figures here, so we're going to want to round this number to 203 kilopascals because we have a 6 afterwards. Okay, now what if not only does the pressure have an impact on our system, but what about temperature as well? Or what's the relationship between pressure and temperature? Well, I'll give you an example, a situation. You can kind of ponder it, and then that will help you understand what's going on. So let's say we have a warm summer day, and we want to know what happens if we have a balloon, it's inflated, and we take it from inside in our nice air-conditioned outside into the heat. So So I have my balloon, it's normal size. I take it outside, my sun is beating down on it. The energy from the sun is warming it up because energy is heat. Okay, I have a low temperature to begin with, then I come up and I have a higher temperature. As my temperature goes from low to high, I notice that my volume of my initial balloon has now increased. So my V2 is bigger than V1. So V1, my initial volume, is smaller than my second volume. My initial temperature is smaller than my final temperature. So I want to know what kind of relationship is this between my volume and my temperature. If my volume increases, as does my temperature, then, you just love the camera, don't you? As my volume increases and my temperature increases, because they're both increasing, they're going to have a direct relationship. So as one increases, as does the other one. So moving on then, to measure temperature for regards to pressure problems, we have to use Kelvin, because the Kelvin temperature of a substance is directly proportional to the average kinetic energy of particles. So remember that the Kelvin scale is based off of absolute zero, being 0 Kelvin, and that's when we say that particles stop moving. So if particles have stopped moving, there's not going to be any pressure exerted by those particles because they will have stopped having collisions with each other and therefore stopped putting a force on something else. So that is why we must measure temperature in Kelvin. To do so, we have our degrees Celsius plus 273 is going to give us our temperature in Kelvin. Okay, because 0 degrees Celsius, the freezing point of water, is equal to 273 Kelvin. And that's how we get that relationship. The next thing I want you to do is practice converting from Celsius to Kelvin, as we'll have to do that multiple times with our gas problems. So if we start by first converting 0 degrees Celsius to Kelvin, you should have got the answer of 273 Kelvin for that one. Next, we'd like to convert negative 32 degrees Celsius. That we get 241 Kelvin. Next, 22 degrees Celsius to Kelvin. Again, we're just adding 273 to our degrees Celsius. And I get 295 Kelvin. This is what we like to approximate room temperature is, or sometimes they also approximate room temperature as 25 degrees Celsius, which is 298 Kelvin. Okay? Notice that there's no degree sign with Kelvin, it's simply Kelvin.